In this video, we'll give an introduction to substitution. Now, to start off with some motivation here, recall that the chain rule of differentiation is used for differentiating a composite function. So kind of a simple example here is if we have the derivative of sine x squared. So this is a composition. We typically look at this and we see the inside function x squared and we think of the outside function sine. In words, the chain rule will tell us we take the derivative of the outside function, evaluated at the inside, multiplied by the derivative of the inside. Now, once we have this differentiation formula here, we can of course restate this in terms of an antiderivative. This is equivalent to saying that the antiderivative of cosine x squared 2x is going to be sine of x squared plus c. And we can view this much more generally as well. If we think about just applying the chain rule to a composition, the derivative of f of g of x, so we have our inside function g, our outside function f. The chain rule tells us we take the derivative of the outside function, evaluated at the inside, multiplied by the derivative of the inside. Now making the corresponding statement for an antiderivative, flipping this around, the antiderivative of f prime of g of x times g prime of x is given as f of g of x plus c. And this leads us into what we can think of as the method of substitution. Substitution is going to be an integration method that undoes the chain rule. And typically what we're going to want to do is evaluate integrals of this form, f of g of x times g prime of x. So this is something that I would say looks like it has been differentiated with the chain rule. And kind of the key observation to make here is you see this function g of x and its derivative appearing outside. So you have that function derivative pair appearing inside the integral. In this case, the substitution u equals g of x is going to transform this maybe difficult looking integral in terms of a simpler, easier to evaluate integral. And how we take care of this g prime of x dx is we think in terms of differentials. So if u is g of x, du dx, a derivative of u with respect to x, is equal to g prime of x. So du is just g prime x dx. So the g of x becomes the u, and the g prime of x dx becomes a du. Let's make a few observations. So what substitution does for us is it's not something that solves the integral, so to speak, but it allows us to start off with a possibly complicated integral, what we have on the left here, and to express it in terms of a simpler, what is hopefully going to be an easier to evaluate integral. Kind of the indicator in terms of when it's a good idea to apply this u substitution method is we look for, as we mentioned on the previous slide, this function derivative pair appearing. So we see something where we have the function g of x, which is kind of inside, and then we have g prime of x appearing outside of that function f. That is a great indicator that we might want to try a u substitution. A very important observation here is to make sure that when you're applying a u substitution, what we are doing is we're starting off on the left with an integral only involving the variable x, and when we rewrite it via the substitution, we get an integral on the right which only involves the variable u. So there can be no middle ground here. We're not allowed to mix our variables together. All x's in the beginning, after the substitution, all u's. Kind of a corresponding statement to that would be if we're applying a u substitution to a definite integral, you must, and I really emphasize here, must change the limits of integration. And the reason that that is the case is because on the left here we're going all in terms of the variable x, so what we get on the right here has to be all in terms of the variable u. And if we left those limits of integration on the right here going from a to b, that would be x equals a to x equals b. And that's not a mathematically correct statement. So we need to go all in terms of x, including the limits of integration, to all in terms of u, including the limits of integration. And the practice problems will give you a few great examples of this. So let's finish by looking at what's hopefully a very simple example. So kind of the indicator here that we might want to use a substitution is we see this x squared, which is inside a function, the cosine function, and its derivative, the 2x, appears outside. So that is a great indicator that we would want to apply a substitution. So typically what we're going to do is we're going to pick u to be a function which is inside something else, so u is x squared, and then in this case du is going to be 2x dx. So we're starting off with the integral of cosine x squared times 2x. And we need to convert this solely in terms of the variable u. So the x squared inside the cosine becomes a u. The 2x dx outside of that cosine function becomes the du. So this is the integral of cosine of u du. So we've applied the u substitution. As we mentioned, it doesn't solve the integral for us, but what it does is it allows us to express it in terms of a simpler, in this case much easier to evaluate integral. Antiderivative of cosine is sine, so this would be sine of u plus c. And another really important observation to make here is that when we apply substitution to an indefinite integral, our last step is always going to be resubstituting. So the question was originally phrased in terms of this variable x, so the solution we give needs to be in terms of the variable x. So we simply go back to what u is equal to, x squared, and we resubstitute that back in. So this is equal to the sine of x squared plus c. Now I'd say this is a very simple but typical application of the method of integration known as u substitution.